All right, I'm going to try number 36. This question asks me to plot the graph, quantity x minus 1 to the 5th power plus 4, only looking at the interval from -1 to 3. And it asks me to trace, find the maximum and minimum features, basically just kind of scan out what's happening here. So to go to my graphing calculator, basically I'm going to have my window go from -1 to 3 because that's all I needed, and because I know what kinds of values the graph is going to have, I'm going to have it go on the y-axis from -35 to 50. And so if I graph this thing, you see the graph comes in looking something kind of like that. Now honestly, I'm not going to completely trace this. It asks for maximum and minimum values. I can see the maximum value is going to happen over here when x is equal to 3. The minimum value on the interval, which is actually a little bit off here, is going to happen over here when x is equal to -1. So I just went ahead and found those functional values. F of -1 is -28 when you substitute back into the function. So -1, -28 is a point there, and that'll be the global minimum value, by the way. And then f of 3 is 36, and 336 will be the global maximum point. Coming back here, asked me to trace along here and estimate maximum and minimum values, that type of thing. Actually, the only thing you notice here is that as I come along here, it appears that I have a graph going, the graph is going up, levels out, and then continues up again. So that would be what appears to be a plateau point there at 1, 4. Also, notice the concavity is down, and then the concavity goes up. So that would not only be a plateau point, but it also appears that the point 1, 4 is a point of inflection. And so that covers everything that I can see just kind of looking at my graph. And now I'll go to the board and we'll look at more specifics with the first and second derivatives. All right, got to take a look at part B of question number 36. You can see my function here. It asked me to take my first and second derivatives and to try to determine what that tells me about the things I observed, basically backing up whether or not my observations were correct, if there's anything we missed, that type of thing. So the first derivative here, really easy one to take. Just apply the power rule here. That's 5 times quantity x minus 1 to the 4th. Derivative of the inside function is 1, so that doesn't change anything. Derivative of 4 is 0, so we're done there. I want to find out where the derivative is equal to 0. Now keep in mind, critical values, it's a little bit different in this case because we're looking for values where the derivative is 0 or undefined. Okay? It's going to be undefined at the two endpoints. So technically we do have critical values on this thing happening at -1 and 3. Again, not something we've made a real big deal about, but there could be some places where that actually is kind of important to keep in mind. So maybe not with concavity and whether or not the graph is increasing or decreasing, but for example, finding minimum and maximum values, those could happen at the endpoints. So we do want to take those into account. So where is the derivative equal to 0? Well, derivative, of course, is going to be equal to 0. We can divide both sides by 5. Point here is this is a product. It's going to happen when x is equal to +1. That's the only place where that derivative is going to be 0. Now, it's going to be undefined at the endpoints because the graph basically cuts out. We don't have the same slopes basically as you approach from one side as from the other side. So technically when you make your number line here for f prime, you're going to have a point at -1, which is basically just an endpoint. In your book, usually just puts an EP there to represent that that's an endpoint. We're going to have a point at 1, and then we're going to have a point at the other endpoint at 3. Again, you can mark that as an endpoint. So your graph really doesn't exist on either side of that. I don't really need to check anything there as far as slopes. I really just need to check values between 1 and 3. So I can put a number like 2 in here. If I put 2 in there, that's going to give me a value of 5, which is positive, so the graph is increasing. Interestingly, a lot of times we expect this to go down and then go back up, but you'll notice when I stick something like 0 in here, I get a negative, but that becomes a positive when you take it to an even power, and it goes up as well. So actually what ends up happening here is that's actually just a plateau point, and if you remember from the calculator, that's exactly what the graph did. The graph basically came through and it leveled out like this and then went back up again. And that was happening when x was equal to 1. And so we saw that point there. I think it was the point 1 comma 4, if I remember correctly. So that's the idea basically coming from the first derivative. And so now I can find other critical values. I can find f double prime. So technically the critical points, the coordinates of those points where we have those critical values, it would be at -1, I believe it was -1, -28. We had a point here at 1, 4. And we had a point over here at 336. And those are all key points on this graph because it's the lowest point, which by the way, that -1, -28 is the global minimum. Okay. Meanwhile, at 336, we get the global maximum. So the point here is endpoints matter. Okay. Just because I don't have a change in the sign of the derivative here, the graph is continuing upward forever, and that highest point is going to happen where that graph ends. Meanwhile, here it's going downward forever at -1, -28, and that lowest point is going to happen where that ends. So endpoints do matter, and that's something that they wanted to look at in this problem. Now, for the second derivative part, I'm going to take this chart out here so we've got a little bit of extra space here. And for the second part, I can find the second derivative here. Second derivative, really easy to work with as well. Again, apply the power rule. It's going to be 20 times the quantity x minus 1 raised to the third power. We can set that equal to 0. And the same kind of thing is going to happen here. This is a product. Only value that's going to be able to make that equal to 0 is x equals 1. Again, it's going to be undefined at the endpoints of -1 and +3. So when I make my number line, technically, you want to put those in there as values to consider for different things when we're analyzing the graph. So basically, we have a point here at 1, we have one at -1, and we have something at 3. And again, the graph only exists between this range. So basically, I can substitute something in between 1 and 3, something like 2, which gives you a positive value. The second derivative, concave up. Meanwhile, over here, if I substitute something like 0, and you get a negative to an odd power, which will give you a negative. And so as a result, that's concave down. And again, you can see this graph concave down until it gets to 1, levels out, and then it goes up here. Notice, change in signs of the second derivative. That, ladies and gentlemen, is a point of inflection. So I do have an inflection point there where that concavity changes. You can see that very clearly on the graph, and now I have the background for that. Now, if you look at the other part of the problem, I found the equations for the first and second derivative. We talked about those critical values there. It does ask me how the second derivative test applies here. Okay, the second derivative test, relatively easy to work with, and it basically says two things. If f prime of x is equal to 0. In other words, if this thing has the possibility of having hit a relative minimum or a relative maximum, then I can check the second derivative. Okay? So, in other words, if your graph has the possibility of having done something like this or having done something like that. Now, it could also be a plateau point. Okay? But, if the second derivative is greater than 0, okay, what is that telling you? It's telling you if the concavity is up at that point, you get a minimum value. Okay? Meanwhile, if the derivative is 0 and the second derivative is less than 0, you get a maximum value. And again, that should make sense because if the second derivative is less than 0, it's concave down, which means you're going to hit a maximum point like that. Okay? And meanwhile, if the second derivative at that point is 0, there's just some kind of question. So notice here, at that point, if I go find the second derivative here, when I substitute in +1 into my equation here, I get an answer of 0. The second derivative, f double prime of 1 is equal to 0. And basically what happens there, the second derivative test is non-committal. we don't necessarily have a maximum or a minimum. In actuality, what does that mean? It means we have that plateau point there. So the graph didn't hit a max or a min. So that's the idea of the second derivative test. And basically, Part D asks me to explain how I know that there aren't any other critical points or points of inflection. Well, we found all the places where the derivative and second derivative were equal to 0 or undefined. So there are no other places where this graph could have any turning points or where the concavity could have any kind of change. So we know that we've covered everything. So that's what they're shooting for in Part D. Hope that helped.